Hello, welcome to GG and OCN 312. The topic of the class is Advanced Mathematics for Engineers and Scientists. In this lecture, in this video, I'd like to cover a review of elementary functions. We'll first talk about polynomials, and then exponentials and logarithms, followed by trigonometric and hyperbolic functions. As a review, my main objectives for you in viewing this video, as well as doing the homework problems or the problem sets related to these functions, is for you to become refamiliarized with them. Mathematics is a language, and like any language, we need practice. And so by seeing these functions, I hope to jog your memory and your familiarity with them so that you'll come out being more confident with manipulating them and using these functions. Okay, so the first type of function is polynomials. And actually, before we get into polynomials, let's just talk about the situation where we have y being a general function of x. So in other words, y is the value of that function evaluated at point x. Right? So if we discuss y being of f of x like this, then we'll often refer to y as being the dependent variable and x being the independent variable. So in that sense, it's often convenient to think of varying x, and therefore, how does that influence what y is, right, being this function of x. So let's start from a very basic function, a function that you're all very familiar with, and that's a function of a line. So we might draw x being the independent variable on the horizontal axis and y, the dependent variable, being on the vertical axis in this case. And when we do that, we can sketch our line, as such. And when x is equal to 0, we have an intercept, which we can refer to as b, and the slope of the line is m. Right, so the function of x is mx plus b. Okay, and so a line, as you know, is a first-order polynomial. Where the order refers to the exponent on our independent variable, in this case x. So we have x raised to the first power, so this is a first order polynomial. And being a first order polynomial, this means that the function is proportional to y, and it increases linearly with it. Okay, so maybe I've sort of beaten that to death, but I do that because I'd like to relate this to a general polynomial. So the general n-degree polynomial we can express as f of x being equal to a coefficient a sub 0, x to the n plus a1, x to the n minus 1 plus a2, x to the n minus 2, etc., all the way down to a sub n x to the 0 power, or which is, of course, 1. And we can, in general, equate that function. Generally, it's equated to 0. So this is our general n-degree polynomial. Now, the order of the polynomial is the greatest exponent on x that has a non-zero coefficient. Right, so we talked about our line as being a first order polynomial. A parabola, for example, would be a second order polynomial. So, for example, if f of x is equal to ax squared plus bx plus c, this is, again, our second order polynomial. And the second order polynomial has two roots, or two solutions. That is, the solution of f of x is equal to 0. Right? So the order of the polynomial also determines the number of roots, or solutions, that f of x equals 0 will have. Okay, so that's enough for polynomials. Let's move on to exponents. So a function involving an exponent, f of x, would describe a constant a raised to the x power. And if x is an integer, a simple way to interpret this is that we're multiplying a by itself x times. So let's talk about rules of exponents. So if we have a raised to the x power multiplied by a raised to the y power, then that product is equal to, or can be expressed as, a raised to the x plus y power. Right? And an easy way to understand that is, for example, let's say x is equal to 3, y is equal to 2. So we're first multiplying a by itself 3 times, right? That's a to the 3 power. And then we're multiplying that by a multiplied by itself twice. And you can see that the solution is obvious, right? It's a to the 5th power, a to the y plus x power. So a related rule is when we have a to the x divided by a to the y, and that is equal to a to the x minus y. And you can imagine if we take the same example, if we have a cubed divided by a squared, then the result is a to the first power, right? A to the 3 minus 2 power in that example. Okay, the other rule of exponents that I'd like to review is if you have a raised to the x power and you raise that whole quantity to the y power, then the result is a raised to the x times y power. Okay, so we have a multiplied by itself x times, for example, and then we're multiplying that product by itself y times. So that's a to the x times y. A times b raised to the x power is equal to a raised to the x power, b raised to the x power. So this represents a situation where the order of the multiplication doesn't matter. We can multiply a by itself x times, followed by multiplying b by itself x times. And that's equal to multiplying ab times ab x times. Okay. So this is a general exponent function, exponential function. There's a very special exponential function when a is equal to e. E, or the exponent, is equal to something like 2.71818, and it goes on basically forever. And this number is, well, it's about as special as the number pi. It's so widely used, and it appears in so many equations. And E is defined as the limit as n goes to infinity of 1 plus 1 over n raised to the n power. And it's also the solution to the following equation, the following differential equation. df dx is equal to f of x. In other words, if we take the derivative of f with respect to x, we get the function f back. And the solution to that differential equation is e to the x. E to the x has this property. Now let's talk about logarithms. So the log is the inverse of an exponent. Right? So, in other words, if, for example, m is equal to a raised to the x power, then the log tells us, well, x is equal to the log base a of m. Okay, and I've written the subscript a to represent the base of the logarithm. Okay, this tells us that m when raised to the x power, this tells us that x is the log of m when a is raised to the x power, so a being the base of the log. Now, if a is equal to e, then, oops, my e disappeared, then log base e is referred to as the natural log. And that's often written as just ln. That is, the natural log of m is equal to the log base e of a number, in this case m. So now let's look at some rules of logs. So we've already established an example. So we've already said that m is equal to a raised to the x power. Let's define another number, n is equal to a raised to the y power. So m is equal to a multiplied by itself x times, and we're just going to say here that n is equal to a multiplied by itself y times. So the first example is what happens if we multiply m by n. If we do that, we see that we have a to the x power times a to the y power. So we have a multiplied by itself x times a multiplied by itself y times, so that's a to the x plus y power. And if we take the log of that, we see that the log, that is base a, of the product of m and n is equal to x plus y. And the log base a of m is equal to x, the log base a of n is equal to y, and so we have verified our first rule, that the log base a of m times n is equal to the log base a of m plus the log base a of n. Now let's look at a second case, and this time we're going to divide. And division is just like multiplication. We treat it just like multiplication. But instead of adding two exponents, we subtract the exponents. So we have a multiplied by itself x times divided by a multiplied by itself y times. That's equal to a to the x times a to the minus y, and this is equal to a to the x minus y. So again, if we take the log base a of our quotient, we see that that's equal to x minus y. And so this brings our second rule, and that's the log base a of m divided by n is equal to the log base a of m minus log base a of n. Now the third rule is the log of a, or log base a, of m raised to the p power is equal to p times the log of m. And the fourth rule is that the log base a of m is equal to the natural log of m over the natural log of a. So let's look at this one. So we're going to take the log of m, the natural log of m, and we know that the natural log of m is equal to the natural log of a to the x, and by rule 3, that's equal to x times the natural log of a, right? That's rule 3. So if we solve for x, we see that x is equal to the log of m divided by the natural log of a. And again, x was equal to the log base a of m, and we've verified our fourth rule. Okay, so the last set of functions I'd like to review is trigonometric functions. Right? And I'll go ahead and sketch this out. This is a review of basic trigonometry, but we can draw a set of axes on our Cartesian plane and draw a unit circle centered on 0, 0, right? And right, so this has a radius of 1, our unit circle radius. And if we look at a certain point on that circle, and we draw a radius arm connecting that point to the origin, that the angle between that radial arm and the horizontal or x-axis is theta. Okay. And if you recall your trigonometry, the x value of that point is equal to cosine of theta, and then the y value of that point is equal to the sine of theta. Okay, so this point is point x, y on our unit circle. And so that's one of the basic ways you were probably introduced to trigonometry. But what I would like you to be able to do is relate that geometric relationship to how cosine and sine vary with theta. So here is, so the vertical axis is the value of cosine and sine, and of course cosine and sine vary between 1, positive 1, and minus 1, and they vary between positive and minus 1 over the interval of theta going from 0 to 2 pi. Right? So let's consider sine theta first of all. So when theta, again, this is, let me make sure you know, this is the theta axis. And so when theta is equal to 0, right, then we're right on the x-axis. So sine theta is equal to 0. And as theta increases to 90 degrees, sine of theta increases to 1. So 90 degrees being pi over 2. And then as we continue around our circle, the sine of theta decreases back to 0 at 180 degrees, right? And then as we continue around this side where theta is greater than 180 degrees, then sine of theta becomes negative. Okay? Right? And we can do something similar. I'd like you to be able to connect how cosine varies with theta. Again, when theta is 0, cosine is 1, and cosine decreases to 0 when theta goes to 90 degrees, or pi over 2. Cosine is minus 1, where theta is all the way on the other end. That's theta is equal to pi. And then it comes back up to positive 1 as we continue to wrap around. Sorry about my poor sketches of these functions, but I just want to make sure you have those images sort of ironed into your thinking. And so through geometry and other reasoning, there are many relationships between the various trigonometric functions. And I encourage you to review your trig identities in whatever, I mean, you can find tables easy enough online, or you can, of course, refer back to your favorite trig or calculus book to do that, because you're going to be using these trig identities to solve some of the problems in our homework assignments and throughout the class. So now let's talk about hyperbolic functions. So trigonometric functions describe the relationships between the x and y coordinates to theta on a unit circle, right? And you might recall that a unit circle is described by the equation of x squared plus y squared is equal to 1. You might also recall that a circle is a type of conic section. Now, another type of conic section is a hyperbola, right? And that can be expressed by the equation of x squared minus y squared is equal to 1. So like trigonometric functions that relate x and y to angle theta, hyperbolic functions relate x and y to an angle about a hyperbola. So let's sketch a hyperbola so you have a sort of a visual picture of what these functions mean geometrically. So again, I'm sketching my x and y axis. And I'm also going to sketch two lines, x having a slope of 45, or having a slope of 1, an angle of 45 degrees, because these two sets of lines are what bound the hyperbola. And so the hyperbola has a y-intercept of +1 and -1, and it is, again, they asymptotically reach these two lines. Right, like that. Okay, so these are our hyperbolae, and so we'll sketch a point x, y, and as with our circle, we'll sketch an arm going from the origin to that point, and the angle that arm makes with our horizontal axis. Let's just call that alpha divided by 2. And with that, the y value of that point is equal to the hyperbolic sine of alpha, sinh alpha, and the x value see if I can draw it like that, is equal to the hyperbolic cosine of alpha. So the geometric relationships are analogous to the trigonometric functions. Now let's write out the hyperbolic cosine of x, and we can write that out as e raised to the x power plus e to the minus x power all over 2. Since the hyperbolic sine is equal to e to the x power minus e to the minus x power divided by 2. And we like our trigonometric functions, we have a hyperbolic tangent of x, and that's equal to sinh x divided by cos x. And I'll remind you that our tangent of theta for the trigonometric function is equal to sine theta over cosine theta. So we'll talk more about, well, you'll get practice plotting and manipulating hyperbolic functions in the homeworks, but I'd like to refer you to page 3 of Sham's outline. And that's the PDF for that is on the course website, as well as page 1118 to 1119 of Greenberg's text. Okay, so that does it for hyperbolic functions. So the very last topic I'd like to discuss is odd versus even functions. So an even function describes a situation when the value at positive x is equal to the value of the function on the other end of the x-axis, at minus x. F of x is equal to f of minus x. So in other words, it's symmetric about x equals 0. An odd function is described by f of x being equal to minus f of minus x. In other words, it's anti-symmetric about x is equal to 0. So an example, actually, let me ask you this. So if we have cosine x, sine x, why don't you think to yourself which one is odd and which one is even? Okay, so I hope you can answer that question I'm posing to you. So the other aspect of functions is any function can be broken into an even and an odd part. Or it can be described as the sum of an even and odd part. So a decomposition of f of x into an even part can be written as the even part, represented by capital E of x, plus the odd part, represented by capital O of x. And that is done simply by taking f of x plus f of minus x divided by 2. So it's the mean of f of x and f of minus x. That's the even part. And the odd part is f of x minus f of minus x over 2. Okay, so we have 2 f of x's divided by 2. When we add those together, we get f of x. And then we add f of minus x divided by 2 minus f of x minus 2. So we're still preserving our original function, right? We're just showing how we can decompose it into this odd and even part. Now, of course, it may be true that the even part is 0, right? If this part is 0, then the function is odd. Right? Or it may be true that the odd part is equal to 0, and then the function is even. Okay? So let's look at, why don't I ask you a question here, and you can work this out by yourself. So cosh of x, as I mentioned, is equal to e to the x plus e to the minus x divided by 2. And sinh of x is equal to e to the x minus e to the minus x divided by 2. So is cosh odd or even? And is sinh odd or even? So this would be a time to, for example, stop the video and think about this question that I've raised and work this out for yourself. But now, assuming you've done that, I'll just talk about the answer, right? So we can transpose the sign on x, right? So if x is equal to positive x, then we can see cosh for x is positive is equal to itself when x is negative, right? Because we're adding both the positive and negative terms here. So cosh is even, and sinh is odd. Right? So for example, sinh of positive x is equal to e to the positive x minus e to the minus x over 2. And sinh of minus x is equal to e to the minus x minus e to the x over 2. And from that, you can see that sinh of x is equal to minus sinh of minus x. Okay. All right. Well, hopefully this review helped sort of jog your memory and sort of helps you think about these functions, and you'll get to have some practice in working with them in the homeworks. So that'll conclude this video.